Okay, we're going to call this particular mini lecture Chapter 21, an interlude, and it's going to be called, as a subtitle, It's All Mechanism. What it really is doing problem 53 out of Chapter 21, step by step, because that's a great mechanism problem that's going to illustrate some fundamental principles. The problem as it's written in your textbook is, of course, line structure. You take this molecule, you add it to this particular molecule that's called an oxime, and acid catalysis, and what they're saying you get is this little beast. Kind of odd. We wouldn't know how to name this, and that's a darn good thing. So the instructions say, propose a mechanism. Alright, so with mechanism problems you have two choices. You can start from the beginning, or you can start from the end. I'm going to look at the whole big picture. I'm going to see that I have an ester here and an ester here. I see that I have a more electrophilic ketone and a less electrophilic ester. I see that I have a fantastic nucleophile. In fact, what I see about that nucleophile is that both the nitrogen and the oxygen are nucleophilic. And I think, going back to chapter 1, oxygen being more electronegative is going to be less nucleophilic. Okay, so I've got a whole bunch of stuff going on here. Nitrogen is the better nucleophile. The ketone is the better electrophile. And I'm just going to guess that that nitrogen-oxygen bond is the same as that nitrogen-oxygen bond. Could be, might not be. And I'm similarly going to guess that that ester linkage is the same as, well, is related to this ester. So that said, let's get started. Okay, what am I going to do? Of course, I'm going to translate into non-line structure. And if I'm going to have this guy attack, this is not a phenomenally nucleophilic nitrogen, and as you will recall, we're under acidic conditions. So, first step in the mechanism is most likely protonation of the ketone. At which point you should say, well, why does the ketone get protonated? Well, because I want it to. No, that is not the reason. Why doesn't the ester get protonated here? It does. Why doesn't the ester get protonated there? It does. All these protonations and deprotonations are taking place in the beaker full of 18 bazillion molecules. But eventually, I'm going to get protonation on my ketone, which of course makes it even more susceptible to nucleophilic attack. And that is when my nucleophile, this nitrogen, can zoom up here and react to make the tetrahedral intermediate. Okay, so what's happening here? I am on my way to making an imine. And I can't remember, I think this is chapter, well, who knows what chapter this is. It's old stuff. And what's going to happen next? We're under acidic conditions. What's my conjugate base? Well, they didn't specify what the acid is, but the conjugate base of that acid is probably what's going to be my base. I'll just use a generic B for base. So deprotonate here, and I'm going to go ahead and show at the same time. I'm going to convert that into a good leaving group. So pay close attention to the fact that I am really careful about whether I'm under acidic or basic conditions. Okay, so there we go. I've made a good leaving group. When I have a good leaving group on the same carbon as something with a lone pair, I think you know the routine. You're going to push that guy out, and that is going to take us to a next page. That should take us to this guy, where I now have my protonated imine type thing. So of course we're going to deprotonate that, because that's what we do. When we see something that's protonated, we deprotonate it. Alright, so here we go. We have this. And of course, at this point it looks like a pretty nice product. But you have to stop and say, what can happen next? In other words, is there a nucleophile present? Is there an electrophile present? And absolutely, there's an electrophile there. Yeah, well, there's an electrophile here too. Okay. Is there a nucleophile present? Absolutely. And under what kind of conditions are we? We are under acidic conditions. So, seems logical that now, if this guy gets protonated, I'll do some erasing here. If that guy gets protonated, then we are all set up for an intramolecular reaction. So, here's my nucleophile. And now I'm just going to move things around a little bit. Same molecule, I've just protonated my carboxyl oxygen. And so 1, 2, 3, 4, 5, I'm perfectly situated to have an intramolecular reaction. Takes me to this tetrahedral intermediate. Don't like that. Gotta get this a little tidier here. Gotta be real precise with our electron movement arrows. Alright, so here is our current intermediate. Okay, now things to point out. A number 1, you need to deprotonate that hydroxyl group. B number 2, that is a hemiacetal carbon. A carbon with 2 singly bonded oxygens is not nearly as stable as a carbon-oxygen double bond. So you know where to go with this. To the next page. These pages need to be bigger, I think. So we have this guy needs to be deprotonated. So we'll do that first. And that'll take us to here. And then it's just a matter of trying to figure out what's going to happen here with that hemiacetal carbon. And what happens next is I'm going to convert one of these guys into a good leaving group, that one or that one, and the one that's going to leave is the one that's going to allow me to turn this whole thing into a carbon-oxygen double bond. So needless to say, that means I need to protonate the ethoxy group. Because if I protonate the ethoxy group, then, and now I can cheat and go back to my line structure, I should say, sorry about that. Go back to my, well, half and half here. If I protonate my ethoxy group, then I'm really perfectly set up to deprotonate the hydroxyl and get to my product in, as we like to say, one swell foop. So, questions you should ask. Well, you know, why doesn't it protonate here? Well, it does protonate there. That would be taking you right back to where you started from. Why doesn't it protonate here? Well, it could protonate there, but it's not going to lead it as efficiently to product. So you play with all these pathways until you get to the final stable product as shown. So that's our interlude. We'll move on to the next section in our textbook on chapter 21. Let's see what's next.